The Soviet-era Luna 3 was the first spacecraft to use gravity to change course to photograph the dark side of the Moon. The NASA Mariner 10 mission used the technique to swing by Venus to target Mercury. The gravity assist or slingshot maneuver has become a standard for navigating the solar system, with our probes reaching further, faster and more accurately than ever before. The Voyager mission started by chance over 40 years ago, when Michael Minovich, a mathematics PhD student, decided to tackle celestial mechanics' holy grail. It was known as the three-body problem, as it looked at the Sun, a planet and a third object traveling in space, and how gravity from the two objects affected the trajectory of the third. Minovich was eager to take advantage of IBM's latest computer, the 7090. This computer was a second-generation transistorized version of the IBM 709, a vacuum tube mainframe which had a processing speed of around 100 kiloflops per second, unthinkably slow by today's standards. The laws of physics and the conservation of momentum demand that the probe approaching the gravitational influence of the planet and accelerating will then decelerate upon leaving that gravitational field with a net speed increase of 0. However, the probe's speed and direction will change in reference to the Sun. His solution has become known as gravity assist or slingshot. While undertaking an internship at NASA's JPL, he convinced them to test his model using their data. The results confirmed his predictions that if it flew close enough to a planet, a spacecraft could utilize that planet's motion to accelerate itself away from the Sun. When Caltech graduate Gary Flandreau was tasked to see if gravity assist could aid deep space missions to the outer planets, he discovered there was to be an alliance of Jupiter, Saturn, Uranus and Neptune, an event that occurred only once every 176 years, an opportunity not to be missed. So it was decided to launch a mission in 1977. 2 spacecraft would be launched which would slingshot past all 4 of them, a grand tour of the solar system's outer planets in a 12-year time frame. This was to become known as the Voyager missions, and the rest is history.
Ultimately, we're able to put together a picture of where we are in the galaxy and how that environment then influences our environment right here at home. In particular, the radiation environment, which has implications for all sorts of things, including human exploration of space.
Today, those 2 spacecraft have continued on beyond the influence of our Sun into interstellar space, the farthest traveled by a man-made object. This field of influence formed the basis for all future missions, allowing man to set his sights on getting into deep space economically. The Rosetta mission had different challenges: to catch up with and orbit a comet, 67P Churyumov-Gerasimenko. It had a large elliptical orbit around the Sun, stretching from the orbit of Jupiter to within the orbit of Mars. Launched in 2004, a year later the probe passed by Earth for the first gravity assist that flung it towards the orbit of Mars. Two years later, Rosetta grazed Mars, building up momentum, then swung by Earth for a second time, launching it deeper into space. The following year, Rosetta passed by asteroid Steins, before swinging back for a third gravity assist from Earth. And in 2010, Rosetta passed by asteroid Lutetia. Going into hibernation, Rosetta continued its parabolic trajectory towards its final destination. 4 years later, Rosetta emerged from its cold sleep as it crossed paths with the comet, a circuitous flight indeed. The spacecraft then embarked on a series of maneuvers that took it on 2 successive triangular paths. Its trajectory was fine-tuned with thruster burns until it closed in to within about 30 kilometers of the comet, where the spacecraft entered actual orbit around it. Rosetta remained with the comet, delivering it cargo, then conducting science observations as it swung about the Sun, then concluded with a gentle impact on the comet's surface in 2015.
We're going to refine our ideas of what the comet is, where the comet came from, and encapsulate that within our ideas of how the solar system formed. And the complexity of the data set that we have also allows us to be more complex in our ideas and our theories. And that is the beauty of Rosetta, and we're starting to see that happening now, that we're really able to hone down our ideas of how the comet formed, how that fits in the evolution of the solar system, and that's going to continue.
The Ulysses spacecraft had to leave the ecliptic plane of the solar system to study the polar regions of the Sun. Accordingly, it needed to change its orbital inclination. This required a large change in heliocentric velocity, so a gravity assist maneuver around Jupiter was chosen. The giant planet's gravity bent the spacecraft's flight path southward, putting it into an orbit over and under the Sun's north and south poles. The ion-powered Dawn spacecraft took maneuvering a step further.
Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
NASA's latest mission is underway. Osiris Rex is the agency's first attempt at intercepting and touching down on an asteroid. No ordinary asteroid either. Bennu is its name. Orbiting the Sun very closely to Earth's orbit, it has been deemed a possible impact threat in the coming centuries. NASA intends to take a sample of the asteroid and return it to Earth for further study, and possibly help form plans to redirect Bennu. To match the orbit, Osiris Rex made a very close swing by the Earth a year after launch. It passed by the South Pole to change its orbital inclination several degrees to match that of Bennu. Once matching orbits, Osiris Rex must perform a series of braking maneuvers to match velocity and enter an orbit around the asteroid. After mapping and studying the body, Osiris Rex will drop down to the surface and collect a sample of material. With some clever robotics, the sample return capsule will be delivered back to Earth.
Well, the thing that is so intriguing to me about asteroids is that they really are time capsules. They actually are samples of what the solar system was like billions of years ago. Asteroids are small bodies that never got made into something big like a planet. So anything that got made into a planet got melted down, got changed. There were lots of things that went on. Asteroids are pristine. Nothing really altered them for billions of years. So when you go out and you take a sample of an asteroid, you have in your hands a real sample of what the solar system was like billions of years ago. What were they the conditions? What was the chemistry like? What can you learn about the formation of our own planet and ourselves by looking at what the solar system was like billions of years ago? And this sample is incredibly scientifically important. I think that people will be studying it for generations to come.
The Juno space vehicle was launched in August 2011. In 2012, at perihelion, the craft performed some maneuvers out beyond Mars orbit and arched back towards Earth for a kick in speed and direction. In October 2013, it flew by Earth a mere 500 kilometers from the surface. This slingshot sent it on a 3-year journey directly towards an intersection with Jupiter.
Jupiter orbit insertion is probably one of the most important things in the entire mission, and it's because that changes us from being in orbit around the Sun to being captured in orbit around Jupiter. And if you're not in orbit around Jupiter, you can't do the science we want to do. And what we're learning now is even in other solar systems, they don't always all have a monster like Jupiter. And many people think, boy, you almost need a Jupiter to have an Earth maybe. Jupiter played a big, important role. But its environment, everything about it is extreme. It's a planet on steroids, right? It is the most extreme in every way it can be. So it has the strongest magnetic field, the strongest gravity field. It has the most harsh radiation. It's spinning super fast. I mean, everything about it is this extreme environment.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yeah, so this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see. This is the first time we've ever been able to do that.
The 6.7-year, 5 billion kilometer transit journey of the Cassini probe was slightly longer than the direct Hohmann transfer. The mass of the Cassini spacecraft was such that even with the Titan IV launch vehicle, Cassini needed added help to reach Saturn. So, to gain momentum, the Cassini mission included several gravitational slingshot maneuvers. 2 flyby passes of Venus, 1 of the Earth, and then 1 from the mighty planet Jupiter. The Cassini orbiter then spent several years orbiting and maneuvering around the planet and its moons, finally diving through the inner rings of the planet.
When we go into the proximal orbits between the rings and the planet, we've never been there before, and we'll be a little bit more concerned. Here, we've actually been closer to these rings, the Janus Epimetheus ring and the F ring, when we went into orbit around Saturn. So this is not unexplored territory at this point. The nice thing about this, though, is that we've got a much better viewing angle of the rings because of the sun this time around.
And eventually into its atmosphere. New Horizons spacecraft had further to go than Cassini, but being far less massive a probe, it was able to be launched directly towards Jupiter. The spacecraft was launched in 2006 and made its way to Jupiter. Its closest approach happened only a year after its departure, at a distance of 2.3 million kilometers. The flyby provided a gravity assist that increased the probe's speed. It also allowed for a general test of New Horizons' scientific capabilities, returning data about the planet's atmosphere, moons, and magnetosphere. Most of the post-Jupiter voyage was spent in hibernation mode to preserve onboard systems. In 2014, New Horizons was brought back online for the Pluto encounter. It flew 12,500 kilometers above the surface of Pluto, making it the first spacecraft to explore the dwarf planet, and then on into the Kuiper Belt towards its next target, a Kuiper Belt object most likely composed of frozen volatiles or ice, such as methane, ammonia, and water. A future probe to return to Jupiter's moons is destined for another multi-year journey. JUICE, to be launched in 2022, will embark upon a 7-year odyssey, taking the spacecraft via an Earth swing-by, then to Venus, back to Earth with a slingshot to Mars, then back to Earth for a final kick, direct to Jupiter. Heading outward bound is one thing, but launching payloads inward towards the Sun is another set of problems. For example, the Bepi Colombo mission to Mercury, launching this year, will require 9 gravity assist maneuvers. After launch, a 2-year journey using ion propulsion will bring it back to Earth for a kick towards Venus, followed a year later by another flyby of Venus, sending it closer towards the orbit of Mercury. In the following 4 years, the spacecraft will pass by Mercury, tightening its heliocentric orbit until it can match Mercury's speed, and with the aid of chemical rocket motors, insert itself into that planet's orbit in 2025.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system, and a crucial end member because it's close to the Sun, and if you want to get this full picture, you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
Our main target is the environment around the Mercury, especially the interaction between the solar wind and the Mercury magnetosphere.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher. So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
There are 2 more missions in the next year or 2 that will travel further inward than Mercury: ESA's Solar Orbiter and NASA's Parker Solar Probe. Planned for a 2018-19 launch, ESA's solar orbiter will take several gravity assists from Earth and Venus to enter an elliptical orbit resonant with Venus, so that subsequent gravity assists will raise the orbital inclination, resulting in an operational orbit of 25 degrees inclined to the ecliptic plane and increasing to 34 degrees, making direct viewing of the Sun's polar regions possible. During the nominal 7-year mission, the main scientific activity will take place during the near-Sun encounter and high-latitude parts of each orbit, with different science goals planned for each orbit. Together with NASA's Parker Solar Probe mission, it's hoped it will revolutionize our understanding of the Sun, where changing conditions can percolate out into the solar system, affecting Earth and other worlds. Launch window is late 2018. It will use Venus gravity assists during 7 flybys over nearly 7 years to gradually bring its orbit closer to the Sun. At closest approach, the Parker Solar Probe will travel around the Sun at approximately 700,000 kilometers an hour. Some 10 times closer than Mercury, the front of Parker Solar Probe's solar shield faces temperatures approaching 1,377 degrees Celsius. It will travel through the Sun's atmosphere, closer to the surface than any spacecraft before it, facing brutal heat and radiation conditions, and ultimately providing humanity with the closest ever observations of a star. Flying into the outermost part of the Sun's atmosphere, known as the corona, for the first time, Parker's Solar Probe will employ a combination of in situ measurements and imaging to revolutionize our understanding of the corona, expand our knowledge of the origin and evolution of the solar wind, and explore what accelerates the solar wind as well as solar energetic particles. It will also make critical contributions to our ability to forecast changes in our space environment that affect life and technology on Earth.